Hi, today I'm going to show you a reaction that doesn't actually occur in a lab. I'm a computational chemist, and so the reaction I'm going to do is performed purely in the computer. What I'm going to do is take a molecule that I'm making, which will look very strange to start off with, and I'm going to do what we call an energy minimization or a structural optimization, so that the molecule looks a bit more like what we want it to look like. And this is one of the first things that you have to do when you're doing some computational chemistry. So you can see here that I am using a program called Gaussian, and I open up my new window to see what I'm going to make. I am making a molecule called Adamantane. It's made of 4 cyclohexane rings fused together. It's a diamondoid, and it's a rigid but almost stress-free structure. So you can see here I'm making a bond between these 2 carbons, and that makes my first cyclohexane ring. And so far, well, it's looking pretty good. Alright, so I need to add some more carbons to this and make a second cyclohexane ring. I've put the carbons on and I need to get rid of my extra hydrogens and make some extra bonds. So that's the next thing I think that I do here. So you can see now that it's starting to look very weird. This bond is very long and a weird angle as well. But it's the best I can do by just adding this carbon by carbon. Now, of course, Gaussian has an adamantane ring that I could just use, but I'm not going to do that because I'm trying to show you structure minimization. Now, this bond is even weirder because it cuts right through an atom, and so that's a bit of a problem, in fact. I need to clean it up because the program just will not work with it in that sort of way. So I've just pressed the clean button so that we don't have bonds cutting through an atom, but it really doesn't look anything like what I want it to look like. Still, I'm going to save that as my input file, and I'll put it on to calculate, which is going to happen on in the background, so I won't have a video of it actually calculating. We'll have a look at the output file in a minute. Okay, it's finished calculating and I'm ready to open the output file now. Oh, look at it, it's beautiful. You can see the diamond shape, you can see that the atoms are all tetrahedral. If you look at it a bit more carefully and read the intermediate geometries, we can see where we started, which was an utter mess. Look at that, double bonds, single bonds, atoms too far away to be bonded, all rather crazy. But as we go through our 16 steps of optimization, we're going to put some of these atoms closer together and make bonds in the right places. So it's still a bit weird here at step 4, but it's coming closer to what we want. Keep going through the 16 steps. Things start to move into place, bonds start to form, and it starts to look like that 3-ringed structure that we wanted to look like. 4-ringed structure that we wanted it to look like. So yeah, there we go. At the end, it's what we call optimized. It's beautiful, it's low energy, and it's what we want it to look like. And you can see here now the energy that we've gone through from that highly unoptimized procedure to the really nice optimized structure. Tetrahedral carbons everywhere. Beautiful.